Alright, so what we're going to do here today is we are going to look at how we can find the intervals of convergence for power series. Now we're just going to be specifically looking at the intervals here today, but that does not mean that we won't also happen to be finding the center and the radius for the converging intervals. But our end goal here will for all of them be to find the intervals of convergence. For example, let's say in this first case we want to find the interval of convergence for the power series shown. Now remember, it's a power series because it is an infinite polynomial. It has an x in there, basically. If it didn't have an x in there, well, then it would just be an infinite series, but not a power series or an infinite polynomial. Alright, so we want to figure out what portion of x's this particular power series happens to line up with another function. In other words, it converges on another function. So what we're going to need to do is we are going to need to find the center first. Now the center, think transformations, comes from what you're adding or subtracting to x. So this x has been transformed to the right 1 unit, so the center is x equals 1. Next up, we need to figure out the radius of convergence. Now, to find the radius of convergence, we're going to be using one of our series tests. So we want it to converge. The best thing to use is the ratio test. Ratio tests can work for just about anything. Yes, it was occasionally inconclusive, but it can work for all kinds of series. So it's the best place to start. We, though, want to force convergence. So let's think of the ratio test. Ratio test took the limit as n approaches infinity of the ratio of the n plus 1 term compared to the n term. We're trying to force convergence. So what we did is we said, okay, well, when does it converge? By the ratio test. It converges as long as that ratio's limit is less than 1. So that's what we're going to figure out. We're going to figure out when does this happen. So let's go ahead and plug in the a sub n plus 1 term. Notice I've replaced the n's with n plus 1s. And then I rewrote the a sub n expression and wrote it as a quotient. Now I'm trying to force it again still to be less than 1. So now I'm going to clean this up. I need to figure out when this is true. So we'll start by looking at those powers, n plus 1. We're going to use our power properties from algebra and expand those two to be the product of the individual powers. And then that is useful because, excuse me, we can now think of that quotient as being the product of the reciprocal. And notice now we have that negative 2 to the nth in both spots, as well as the x minus 1 to the nth in both spots. They'll cancel. So now we have this simpler expression. What we're going to do is we are going to rewrite it, though, kind of visually separating the non-n terms and the n terms. So the negative 2 and the x minus 1 are both in the numerator. They don't include n. The n, as well as the n plus 1, do of course include an n, so I put them separately. Now I separated them visually because what you want to remember is with the properties of limits, we know that the limit of the product is the same as the product of the individual limits. So that's good because what we can do is now we can evaluate each limit by imagining letting the letter n become infinity. Well, the only one that has n in it is the second portion of the product, I should say. And if I have an n over an n plus 1, that is heading towards 1 as n becomes closer and closer to infinity. Now, as to the other statement, well, there's no n's, so it's going to be the same. It's just going to be the absolute value of negative 2 times the quantity x minus 1, all in absolute value. So let's clean that up one more time. So we want that absolute value to be less than 1. That was our goal. Remember, we're trying to force convergence, and convergence only occurs if the ratio test gives us something less than 1. Now it's an absolute value, so that negative 2 would come out as positive. If I divide over that 2, I now have an absolute value statement. An absolute value statement is a distance statement. This is saying the distance from 1 has to be less than a half. Remember that 1 is the center, so we could also say the distance from the center has to be less than a half. Hence, 1/2 is the radius. Once you get the center statement isolated in your ratio test, the value you see it compared to is your radius. So the radius is 1/2. So now let's go back to what we have so far. We know the center is 1. We just discovered the radius is 1/2. our overall goal now can be achieved. Our overall goal is to find the interval of convergence. So for visual people, let's see a number line. Now we know the center is at 1, the radius is a half, so if I went up a half, down a half, that would give me the end points of my interval. It would be 0.5, comma 1.5, or if you feel like being in fraction mode, we'll do 1/2, comma 3/2. Well, that's great, but I don't know what's happening in either of those two. Should I include them? Should I not include them? Well, I need to test and find out. So that's what I'm going to do. I'm going to test the ends of 1/2 and 3/2 for convergence. Oh my gosh, no! That means I have to do each one separately. So let's say I let x equals 1/2. That means I'm going to put in 1/2 instead of x. So now let's see what happens. Well, that gives me -2 to the nth, -1/2 to the nth all over n. This is a series now, an infinite series. He's no longer a power series, so we're going to use our infinite series tests. Well, I don't really want to leave him just like he is, because I notice both of those are raised to the nth power. So what will I do? Well, I'll use some more algebra and recognize that the product of the bases raised to n, in other words 1 to the nth, will be the same as that product of the individual powers. Well, 1 to any power is of course 1, and oh my gosh, I recognize that. Do you? It's a p-series. So it's a p-series where n equals, n's power equals 1. And by the p-series test, that means it diverges. So I've got 1 down, 1 to go. Now I'm going to let x equals 3/2. I'm going to test the other end. So now I'm plugging in 3/2 for x instead of 1/2. And that gives me -2 to the nth times 1/2 to the nth. Using the same property from algebra I did before, I'll end up getting this time -1 to the nth over n. Well, now it's not a p-series. It is an alternating series. So that was a 2-part test. I need to first confirm that a sub n, the non-alternating portion, goes to 0, and it does as n approaches infinity. Then I need to prove the statement that a sub n is always greater than a sub n plus 1. So I started with that basic statement, n plus 1 greater than n, then multiplied both sides by the reciprocal statements, and that gave me 2 statements that are in fact a sub n and a sub n plus 1. So it is confirmed via that 2-part alternating series test that converges. Okay, so I have both of those 2 tested individually. So let's go back to again what we had so far. Well, what we had so far was the intervals 1/2 to 3/2. Remember, we're looking for an interval of convergence. So based off of the test we've seen so far, at 1/2 we had a diverging series, at 3/2 we had a converging series, so the divergent is not included, the convergent is included because it is a convergence interval. And there it is, we have our answer. Now, that's the more complicated scenario. Let's take a look at another example that will lead to a slightly different end result and see what that looks like. Okay, so this time we're going to find the interval of convergence for this new series. It is a power series because it has an x and an n. So we now have an infinite power series. So what shall I do? Let's start by finding the center. Well, the center is the translation of x. X is not translated, so the center is x equals 0. Next up, radius of convergence. Well, the radius of convergence, again, we can find by thinking of the ratio test. So we're going to once again use the ratio test to force convergence. Well, the ratio test says take the ratio of the 2 terms, the n plus 1 term to the a sub n term. As we approach infinity, if we want it to converge, it needs to be less than 1. Same as last time. So let's go ahead and force that convergence by plugging in our a sub n term, which I have replaced n with n plus 1. So that makes that n plus 2 factorial, and then x to the n plus 1 power. Now there in the denominator, that is of course just my a sub n expression. So let's do a little algebra here. Wait, or algebra 2, perhaps I should say. Those are factorials, so I need to remember how to handle a factorial. Well, in order to handle that factorial, I need to remember that a factorial takes the term, the terms shown, and then 1 less than that, all the way down to 1 as a product. So that means that n plus 2 factorial could be separated to just n plus 2 times 1 less than that, which is n plus 1, and everything below it, hence n plus 1 factorial. Great news, because that will end up allowing those to cancel. Now let's do a little more algebra 1 in this case, because it's just going to be a power property like we saw in the last problem. I'll be able to separate that x to the n plus 1 to x to the n times x. Now we have a bunch of things canceling out and a much simpler limit to evaluate. So we now have the n plus 2 and the x left in absolute value. We want n to head towards infinity. So that means we have something infinitely large times x. And I want to know, when is that less than 1? Well, there are two scenarios here. If x equals 0, then I would have 0 times anything, even infinity plus 2, is 0. And that's true. But if x is anything else, then I'm going to have infinity. Because infinity times anything is going to be infinity. And less than 0. We already talked about that. Well, infinity is not less than 1. That's false. So my radius is 0. If I move any distance away from that center, I have a false statement. So let's go back to what we knew so far. Well, what we knew so far was that the center was 0, and we just found the radius of convergence, which is 0. So moving on to our interval, this is a much easier scenario here. Think of that visual number line. I'm starting at 0, and I'm not moving away from it. So my interval, if you can call it that, is just 0 to 0. 0 is included, of course, because that was a true statement, and we saw that in the last slide. So we're done. No need to test the ends, because we already had done so. All right, now there's one more thing that can happen with these. So let's look at one last example here. Let's say for this last example, we want to find the interval of convergence for this new power series. Looks a little more elaborate, going to have to do a little more algebra. But he's not going to necessarily be as bad as the first one because of what happens. So let's see what happens. Well, of course, I need to find the center first. Looking at the x, there's no translation. X equals 0 strikes again. Now I need the radius. Well, we've done this before. Radius of convergence. Best place to start, ratio test. So that's what we'll do. We will force convergent with that ratio test. So I'm going to again take my limit and make sure it's less than 1. So now I'm going to have my n plus 1th term. But I'm going to go ahead and this time, instead of writing that really complex fraction, I'm just going to go straight to multiplying by the reciprocal. So there's the reciprocal of a sub n. All right. Now here's some good news. Looks very complex, but remember we're dealing with an absolute value here, so I can just ignore that -1 raised to a power in both cases. Sure, they don't cancel perfectly, but I don't care because these are an absolute value and they'll be made positive anyway. So I'm going to get to ignore them. One of the few times in math you can just ignore something and be fine. All right, now, as to the rest, here comes some algebra. So first things first, let me simplify that 2 times the quantity n plus 1. That would become 2 to the n plus 2. So there we go, that's simplified. Now I'm going to have to take those two different concepts we saw in the last slides and do the same thing basically. We've got those factorials there in yellow that we'll have to be able to cancel, and then those powers in green. So why don't we start with those powers? So starting with the friendly algebra, the powers can be separated into the product of the individual powers. Now the factorials. Well, I want to cancel that 2n factorial. Well, I have 2n plus 2, so remember what we said last time. We're going to start with that 2n plus 2 and go 1 less and then 1 less all the way down. So 2 to the n plus 2, 1 less than that is 2 to the n plus 1. That's not the same as what I wanted to cancel 2n factorial, so I'm going to do 1 less than 2n plus 1, which is 2n. That's what I wanted to cancel, so I stopped. Condensed the rest to just 2n factorial. That cancels, along with those powers, which I showed canceling earlier. I've now simplified my expression. So I'm going to do kind of like I did with that first example, and I'm going to group my x's together and my n's together in those two places. And remember, the limit of a product is the same as the product of the limits, so I'll ultimately be taking these two limits products. Okay, well, if I look at the n's, the n, since will be replacing it with infinity, 1 divided by anything infinitely large is heading to 0, so that limit's heading to 0. Well, the other doesn't have any n's, so nothing's going to change. It's just going to stay the absolute value of x squared, which, well, x squared is always positive, so I could just say x squared, but I could keep it in absolute values if I wanted. Now let's finish out here. We have x squared less than 0. Or sorry, times 0. Times 0, not less than 0. X squared times 0 needs to be less than 1. Oh, well, anything times 0 is 0. Oh, snap. That's always true. So if it's always true, that means my radius is infinite. Boom! Fantastic news. Because if the radius is infinite, think number line. I might be starting at 0 for that interval of convergence, but if I start at 0 and go up or down infinity, I'm covering everything. So my interval of convergence is infinite. That power series may, if you recall, or if you don't recall, new fact coming at you, that power series converges perfectly to a trigonometric function. It's one of our 5 basic power series, so perhaps it comes as no surprise that interval of convergence is everywhere, negative infinity to infinity. And those are our 3 cases. We can either have to test the ends, as in the first example. We might not have a real interval per se, as in the second example where our interval was just one meager little point there at the center, or we could converge everywhere, and our power series could actually be the same as another function, where if we graphed it, you may again recall if you've seen this already. If not, brand new fact, as I said before, that is actually the exact same concept as one of your trig functions. And again, if you haven't seen it before, it's going to be one of the 5 basic power series you'll become familiar with in your future. Excellent. Well, hopefully that review of those 3 major concepts helped you out, and perhaps we shall meet again.